And next, substituting for s from equation number 60. From 16. Oh, be clear? 60. Okay. You're going to get I equals 3f I, sorry, 3f by 4 pi, the integration of s, we're going to have p plus q as d mu dt over here. Just keep in mind, simple t is just a changed variable. It's just a variable that we use instead of tau, just for integration purposes, okay? Right, because we don't want to mix the real tau with the variable tau or the optical depth. Anyways, this would be equal to 3f divided by 4 pi times mu plus q. Let's call this equation number 62. Just for the record, we still don't know what q is. It's just some arbitrary constant we had put on. We had put in. Anyway, and going back to some of our previous lectures, using equation 41, the flux coming out of the upper surface of the stellar atmosphere, the stellar atmosphere can be written as F equals 4 pi, sorry, 2 pi, 0 and 1, I, mu, and then substituting from from 62 for I, we're going to have F equals 3F divided by 2 times 1, 3 times Q2 and by just so F cancels out, which means we're going to end up with Q being equal to 2 over 3. Let's call this our 63. Not an equation per se, but a result for Q. Okay, right. Then equation 60 gives you S equals BF divided by 4 pi for us. Now we're going to substitute for Q, all right? For this equation number 64. So many equation numbers, but we need that. And using on equation 64, we can use equations 53 and 56. We're going to write down T U equals 3F 2 plus 2V. And using 47, 48, and 49, we can write down, oh, T to the power 4 equal to 3 over 4, effective temperature to the power 4 times tau plus 2 over 3. So this is equation 65 for us. So the importance of this equation is that it gives, this equation gives the variation of temperature inside a gray atmosphere. A gray atmosphere. Right. Okay. You're not done yet. And substituting equation 63 in 62 gives I of 0 equal to 3F divided by 4 pi and that. Okay, which means now we're going to substitute. Okay, let me just write it down and write. No, actually, F1 pi cancels out. It's going to be 3, 5. Okay, now this, I guess this, it should be obvious what I've done here. I'm just, I'm using this equation to get the I value when mu is equal to 1. Okay, and I'm just substituted then. So I put mu equals 1 here, and you just take the ratio, and you end up with this equation. Okay, this is, let's say, equation number 6. Now, remember, we were working out these equations at the top of the atmosphere, and we're just considering the radiation that is coming out of the surface. Okay, so this is what it looks like if this is your atmosphere. Let's say this is your atmosphere. Okay, like a semicircle. And if you have some radiation coming in this direction, okay, And if you are the observer, and if you are in this direction, you're observing the component in this direction, right? So this would be theta. So we're just considering rays coming out of the atmosphere of the star or the sun to an observer. Okay. Theta is just the cosine inverse of mu. Anyway, I just have to write down that this is a ray coming, let's say, a ray ray traveling. No, not traveling. Directed towards an observer. From the, okay, actually, let's talk about, so it can be any star, right? But let's talk about our sun itself. From the solar disk. Let me call this the solar disk. I hope you get the idea when I say solar disk. Anyway, so let me just keep writing, and I'll explain to you. Suppose, actually, this should be quite intuitive. You'll be able to understand it as you write it down. Suppose we consider the intensity of radiation. The intensity of radiation coming from different points. On the disk of the sun. As seen by an observer. Let's say it's as seen by us. Oh, just in case you can't read my handwriting, what I've written down is that suppose we consider the intensity of radiation coming from different points on the disk of the sun as seen by us or an observer. This is our first point. The next point would be the ray coming from the central point. The ray coming from the central point of the solar disk. Central point of the solar disk emerges out of the solar surface in the vertical direction. So what this means is that theta would be 0, which means mu would be 1. So what I'm actually, let me just repeat, just complete the sentence and read it through. And the specific intensity. And the specific intensity will be I01. Okay, so we are just considering the, well, let me draw it here. We're considering the ray that is coming from the center of the disk at this point. That's the center of this disk, okay? So like that. Then the angle would be 0. Theta would be 0, right? And we are referring to the specific intensity of that, which would be I0, obviously 0 because it's at the surface, and 1 because theta is 0. Okay, right. So I hope that is clear. Okay. Oops. So equation 66 gives the variation of intensity in the solar disk. No, sorry, on the solar disk. On the solar disk as we move from the center to the edge. And as a supplement, let me write this statement as well. This would be less than, for obvious reasons, because theta I is going to decrease. Well, this is true for all mu. So if you go back to equation number 66, as you see, this is the intensity of any radiation at a general angle theta with respect to the radiation that is coming at the center. Sorry, with respect to the specific intensity of a ray that is coming at the center of the disk. Sorry for all the trouble. Sorry. Here we go. Okay, so as we move from this point to this one, towards the edge of the disk, that means this is what we mean by the edge of the disk. The intensity would be decreasing. Okay, and that is kind of our experience too. When you look at the sun, well, looking at the sun is not a good thing, but if you had a chance to look at the sun through some well, polarizers or anything like that, you know that the center of the sun has greater brightness compared to the edges of the sun or the side of the sun that we see. Okay, so this is the explanation for that. Right, I guess it's quite intuitive, but this is the physical and mathematical explanation for that.